Okay, this video is to help you understand the lab activity that we were doing yesterday. And so we have our setup where our cart is on the plane, that's the mass of the plane. We have our hanger on the other side, that's the hanger mass. And now we're trying to calculate the acceleration that is happening in this direction. So in other words, there's acceleration that's happening all through this, and the acceleration that's happening there is the same as the acceleration that's happening over there. Okay, so first thing I want to do is I'm going to draw a free body diagram, and this should look familiar to your notes, but it's always good to listen to it a second time now that you already have it in your notes. But this is my free body diagram that represents the weight, okay, force due to gravity, for the hanging mass. So in other words, my mass now of the hanger times gravity, okay, or 9.8. Now that arrow has to be bigger than this arrow, okay, because the acceleration says net is going to be down. And this I'm just going to label as F of t. It's a tensional force through the string that's connected, okay? Now I'm going to do the exact same thing over here, but this is going to be my mass on the plane. So again, I'm going to draw my, I'm going to switch colors here. My free body diagram, so there's my center of mass, okay, and then I'm going to have my gravity or force of gravity acting down. This is my mass, and I'm going to call it mass on plane times 9.8, okay, and I'm going to have a force normal, and the force normal actually is equivalent to my force of gravity because we're assuming that we're working in a frictionless environment, okay, and that we're not pulling up on anything. And so then the entire force here, okay, that's applied is that tensional force, okay. So in other words, now I'm looking at it in terms of I have a tensional force that's acting in that direction, I have the weight that's acting in that direction, and so I have this net acceleration that's occurring, okay? So in other words, in this instant, because I have a tensional force, my net force, or my force, and I'm going to call it net, the net acceleration force is equivalent to the force that is happening that's tensional between the string, okay? So in other words, this net force is just the mass of the plane object times some acceleration, and that acceleration right there is the same as that acceleration right there, is equal to now my force of tension, okay? I'm going to look over here and I'm going to talk about the same thing on this object. This object has a net force, okay? So I'm switching colors back here. This force, and I'm going to call it net again, is equal to my weight minus my tension, okay? In other words, my weight was just the mass of the hanger times 9.8 minus the force of that tension, okay? And my mass, or my net force, is just the mass of the hanger times that acceleration, and that acceleration is the same acceleration that we have right there. Now again, we have two unknowns, two equations. We're going to set it up and solve for each. So in other words, I'm going to make both of these equal to F of t. Okay, I'm going to switch colors one more time here so I can do most of my calculations. I'm going to say that the mass of the hanger times the acceleration of the hanger is equal to the mass of the hanger times 9.8 minus F of t. Well, F of t is just the mass of the plane times that same acceleration. I'm going to then bring my this piece and this piece to the same side since they both have a's. So mass of the hanger times acceleration plus mass of the plane times the acceleration is now equal to the mass of the hanger times 9.8. Okay? Now the acceleration is the same in both situations, so I'm going to factor the acceleration out, and so I get the mass of the hanger plus the mass of the plane is equal to the mass of the hanger times 9.8. Okay? And then now I can get my acceleration. So my acceleration now is the mass of the hanger times 9.8 divided by the mass of the hanger plus the mass of the plane. Okay? Now this is a way that I can figure out the acceleration in the lab. Okay? This acceleration works for this instance, okay, when we have two objects connected like this on a pulley system. It only works for that kind of a situation. Ideally, we're looking at it from the standpoint of this free body diagram and this free body diagram, and then looking for the relationships between the things that are in common. Okay? Learn that method. If you didn't understand how I got this equation and then derived it all the way down to getting this final thing, we need to sit down and kind of go over how to do that, because that's the important thing. Okay? But ultimately, this is your mass of your hanger, this is the mass that was hanging, this is the mass of what was on the plane. You'll be able to calculate now the acceleration for all of those different trials. Okay? Remember that when you are done with this, you'll want to go back here and go to, oops, the link here, and that link is where you're going to want to go and answer the questions. Okay? And the questions are going to be to look at what was the acceleration value, and this is the experimental acceleration value for each of those. Okay? And then your average percent difference, so how did you do when you looked at these different trials, and then you'll have to answer that question. Part 2, again, you're going to go through and give me the experimental accelerations, okay, the percent difference, and then ultimately, why do we have this percent difference in the first place? Okay, so make sure you answer and submit those, and when you're done with that, you should be moving on to working on some of the friction problems that are on the problem set, and you may want to make sure that you've completed these problems first, because those are problems that should be done at this point in time, and then we'll move on into these, and I'll probably try to get a video posted here as well so that you can have a couple of example problems to work on. All right, and again, be good for the sub.